So we finished that, and we are almost done with this. All right, so I asked the other class, and they seem to be on board with having 2 chapter tests at a time and having the final be comprehensive. What do y'all think about that? The whole semester. Well, I have to have the final be comprehensive because I tend to drop your lowest test grade. So the final has to cover everything. If I do 2 chapter tests, like 2 at a time, should be, I think we have, I'm trying to think how many chapters we have. We got 12, 13, 18. I think it's almost 10. So yeah, probably 5, because usually on the final, I don't have a separate chapter test for what's leading into the final. You know what I mean? I just do that. So it's probably 5 tests total. So we'll have the chapter tests be like the first half of class, because there only be about 20 questions. So they're not very long if we're just doing 2 chapters. So let's see, we'll be finished with this material probably today. Probably today we'll be finished with this material. So let's shoot for next Thursday. Does that sound good for a test? For 12 and 13? Okay. So next Thursday. That's a week from now. And the quizzes will help you prepare. If you want to see what my tests look like, you can go see Miss Steele. She's got all my old tests, all of them. How, and you work with Miss Steele a lot? Does it help? Okay, good. Okay, cool. I talk to her like every day. Okay. So we've been talking about freezing point depression, boiling point elevation. We're going to talk about osmotic pressure. So what is osmosis? Do y'all know? Other than Osmosis Jones, which was an animated film from the 90s, I think. That's okay. Osmosis is the movement of water. So this is the movement of water. And with the movement of water, we have a couple of things going on here. We've got pressure involved, and water moves towards the larger amount of particles. So we would say higher concentration. Okay. Osmosis, movement of water. We're dealing with pressure. There's a pressure force associated with that. And it moves towards the larger amount of particles. One thing I want to talk about that's related to this is what we're mostly going to be focusing on today. I want to talk about vapor pressure really quickly. And then I'm going to pull up some practice problems. Okay, so let's look at vapor pressure, because that's going to be related a bit to water and particles. All right, so if I have 2 beakers, I have a beaker here, and let's say we got a little watch glass on the top, and I have a beaker here, and there's a little watch glass on the top. I'm going to put my water in here. Okay. Let's say one of these is seawater. So I got all kinds of different things in here that make up seawater. And this is just pure, straight up water. Let's first look at this from this perspective. Which one of these has more stuff for the water to play with? This one. So my seawater has particles in there that the water can play with. So let's just say, for our intents and purposes, we've got sodium and we got chlorine, right? Why is water attracted to sodium and why is it attracted to chlorine? Positive, yeah. So what's going on here is we got our oxygens are attracted to that sodium, right? On that water molecule to make that sphere of hydration, right? That sounds like a commercial for Gatorade or something. And then we've got like the hydrogens on here are all attracted to this chlorine. So they got something to play with, right? Y'all ever try to take a toy away or something from a dog that they're not supposed to have, or a toddler? Or you'd be like, what you got in your mouth? Both things, toddler or dog, same response. What you got in your mouth? And they go running, right? Takes a lot of energy to try to get it. That's what's going on with the sodium and the chlorine with the water. You've got these little interactions happening between these water molecules and these ions. So, how does that affect? Think about this. How does that affect water transitioning into gas and liquid? Which one of these is it harder for water to transition from liquid to gas, do you think?
An aqueous solution in like the solvent water, you're gonna have potential for freezing.
Yes, so this has a different boiling point and freezing point. It's different. This one's different. So, how does that affect the gas phase or the vapor that's coming off of that water? Which one of these is going to have more vapor? Which one's going to have less vapor? Is this more or less?
Well, I think you corrected me on the previous class, but whenever I said I think increase the freezing point whenever it was actually decreased. So if the freezing point decreases, the boiling point increases.
Right. So if the boiling point is increased over here, it's going to take more energy to make it to gas phase. So here is a higher vapor pressure because it's easier for that water to become gas. So we got our water gas, it's our vapor, right? You're going to have a lot less going on here. So you have a lower vapor pressure. And we can measure that. We can measure how much vapor pressure is there. We have different ways that we measure that. We can do atmospheres, we can do PSI, we can do torr, we can do millimeters mercury, we can do bars. Let me put my R on seawater. My brain finished that word, but my hand didn't. So vapor pressure is less when you add stuff to water because the water is caught up playing with these ions, right? So it takes more energy to separate the two. So if you had two solutions, you have two salt solutions. Let's say one is 0.1 molar NaCl in water. The other one is 0.5 molar NaCl in water. Which one's going to have the greater vapor pressure? Which one has less stuff in it? This one. These are one of the, yeah.
I heard the opposite of what
That's okay. More vapor, wait, no. I got it backwards. Did I get it backwards? I did it backwards.
Yeah, that's
You know what I did? I looked at the concentrations and I watched and I paid attention to the numbers more than I did the concept. So that's a trap. Our brain looks at larger numbers and thinks more of something. Well, this is more particles. More particles. This is less particles, right? Since there's less particles, more vapor pressure. More particles, less vapor pressure. So that's one of those things you're going to have to correct your brain with sometimes. Like some things seem counterintuitive because of words. So making certain we understand the words and the concepts is going to be really important, particularly when we're looking at numbers. Okay. So let's put it into context over here with movement of water. So if I have, again, let's say I've got a single container. I got a single container, and in between this container, I got a lid on it. I'll just say I got a lid on it. I got a little membrane. Got tiny, tiny little holes in it, right? This is a semi-permeable membrane, meaning water passes through it, right? Semi-permeable membrane, water passes through it. So let's say I got my water like that. On one side, I've got some particles. We could say seawater again if we want to. And on the other side, I just got a little bit. Which direction is the water going to move? To the right, because water moves to where the most particles are. Higher concentration. I'll just put CONC period. Okay. Water moves towards the higher concentration. Now before, I could like put a divider between here if I wanted to. Before I remove that divider and open up that semi-permeable membrane, which side would have a higher vapor pressure? This side. So starting out, this one has a higher vapor pressure than this side does. But eventually, the water is going to move back and forth until we reach something called equilibrium. That's where we have movement of water is at the same speed going back and forth. And it has to do with concentration. It's trying to reach it to where it's an even concentration. It's not always the case with reactions, though. So let's look at it as water's moving back and forth at the same speed. All right. Let's talk about pressure associated with osmosis. So we can measure it in atmospheres, millimeters mercury, torr, bars, psi. I might be forgetting some. This all has to do with the type of instrument that you're using. So depending on the instrument that you're using, that's going to be the unit that you use. So let me pull up y'all's book. I'm gonna pull up your book. We're gonna look at some of those practice problems in there in terms of, okay, in terms of the equations. I want us to look at these equations and see how they work with one another. Okay. All right, key equations. Here we go. All right. We've talked about molality, and we use that with freezing point depression and boiling point elevation. Now remember, because we're dealing with amount of stuff in both things, amount of stuff. Let's look at, there's our freezing point depression and boiling point elevation equations, the exact same equations. The only thing that change are the temperatures and the type of constant that you use. All right, osmotic pressure. Okay, I'm going to erase over here. Y'all remember those billionaires last summer that went into a submarine and it got imploded? Yeah, Logitech controller. Woo! Man, sounds like a collector's item now. Geez, so if you're not hip to the news on that, somebody decided to make, well, a guy that had a lot of money and too much free time decided to make a submarine in his backyard. I call it a submarine in his backyard. That's kind of what it looked like. Y'all want to know what happened? Pressurized with water? Yeah, it was an implosion. So they were in this thing. It kind of looked like this. You got bolted into it. So they had like a metal exterior. I think they were trying to do titanium. And then on the inside, it had a lining of carbon fiber. So here, they got a carbon fiber lining. And then they have this other lining again. And then the people sat inside. They even had a little can for you to go potty in if you wanted to. It was like, what is going on here? So you got people, it's probably more like this. You could fit like maybe 4 people in here or something, right? And then the dude who ignored science. Okay, so carbon fibers, when they're on the single atomic level, behave differently than in bulk form. So bulk carbon is like charcoal, right? So you wouldn't think about lining the inside of a submarine with charcoal because it's very brittle. But if you're talking about single atom height, as far as carbon fibers, really, really thin, they behave differently due to something called quantum confinement. And they can be very, very strong. We can look at carbon in the form of a diamond, right? It can be very strong depending on how it's put together and the thickness of it. But here's the problem. As you go down into the ocean, you've got, thought I got blue, I guess not. You got water that's pushing on this metal all the way around it. And the further down you go, the increased amount of pressure. The increased amount of pressure that happens. So the thing is with that guy, he fired the safety dude, the dude that's in charge of safety and materials, because the dude said, you know, every time you take this thing underwater, you get a little crack in that carbon fiber, right? Little tiny microscopic cracks. Yeah. He didn't like what he was saying. He actually also fired a scientist who this is his bread and butter. And he's like, yeah, you don't need to make your own. Here are companies that already do that. There are at least 2 reputable companies that I know that are in the forefront of deep sea exploration. The inside of the sub doesn't look like that. One person can fit. There's instruments all over the place with sensors for pressure to let you know what's going on. There's also a cord that you have that is retained at the top to where you can ensure communication. Yeah. But with every dive, more microscopic cuts inside this. And they had quite a few successful dives. But whenever you take something like this, put it back in that intense amount of pressure, and you've got microscopic cracks, eventually it's going to implode. So the force of the water goes right in, and it's like crumpling up a piece of paper almost instantaneously. So water pressure is a thing and is part of the reason why we don't just live at the bottom of the ocean all the time, because of the sheer amount of energy and force that's involved with that movement of water. So that crushed everybody on the inside. People are super soluble in water when they're in pieces. So it's like one of my favorite questions that I find on the internet: why don't you find remains at the Titanic site? Like human remains. Oh, that would be good. I think he came out because, there's lawsuits happening now. But the thing is, every person who signed up to go into this, almost every single page has said, you will probably die. You will probably die. Yeah, this is great, man. Woohoo. Yeah, they signed all these waivers, and it's in international waters, so you don't have a jurisdiction. So unless this becomes a UN issue, I don't know. So after a while, but here's the thing, why don't you find human remains at the bottom of the ocean? They've dissolved, they're super soluble, you have animals, you got enzymes, you got acid-base chemistry happening, you know? It's a giant stomach. And then you consider the amount of pressure at the bottom of the ocean, it's just pieces, right? Now, somebody asked me once, well, did they know what was happening? The time it takes for your brain to process that you're in trouble and in pain is way slower than that imploding on itself. It just, like 1 second, hey, I hear something, boom, it's over. It happened real fast. So, yeah. Listen to scientists. For real. If you don't fall down a rabbit hole, look up deep sea underwater exploration. Look at what those things look like, and then compare it to what that looked like. Yeah, because they've got that movement of water, that equilibrium. This is why we see giant squids. Giant squids can live under that type of pressure because that water can move in and out of their bodies pretty easily. Yeah.
I didn't know there.
Oh, yeah. So you got to keep in mind our skin, to some extent, is a semi permeable membrane, right? Our cells have semi permeable membranes. So if you can have free movement within your skin of movement of water to where you reach an equilibrium where you got equal pressure on the inside or outside, you're going to be fine. But we're not deep underwater sea fish. We're not squids either. So it's like,
And also why a lot of those
yep, most of them are blind. They can't see anything.
like no point.
There's no light. There's no light down there. So they don't see anything. So they have different sensors within their body that can detect movement, they can smell, they can do other things. Yeah. So osmotic pressure. You got that movement, same rate, going back and forth. It's going to reach where it's the same pressure on both sides, unless you alter that system. Okay, I'm going to erase this beautiful work of art that I just did. Stick People Theater. Here. I would put like screaming faces on them, but they didn't even know what was happening. So it was like, just, hey, look, we're underwater. Boom, But they knew about it. I mean, the Navy picked up the implosion sound, but the media was like, will they be found? I'm like, nah, they did. Well, that's a good question too. So before the pyramid became the Bass Pro Shop, they used to have traveling exhibits there, like the Wonders exhibits. And in the Wonders exhibits, as a kid, I got to see Ramses the Great, Napoleon the Great, the Etruscans, Catherine the Great. They also had a Titanic exhibit, which felt really creepy, if I'm honest, because it had all of the things that they found when they discovered the Titanic back in the 80s. They had to be careful because those things had been sitting underwater under that pressure. Gosh, for what? It was what, 1914? So for 70 years, that stuff was sitting underwater under that high intense pressure. So when they removed those artifacts, they had to immediately put them into a high pressure environment in order to keep them together. So there are shoes, suitcases, clothes, all of that, because you got that practically free movement between those membranes, right? Suitcase is open, it's not going to implode or anything. It's open, it's water's in there, it's satisfying that equilibrium that's going on. Same with clothes, water passing back and forth. But since it's used to that type of pressure, they have to preserve it in a similar environment. Yeah, I avoid that one. Because it's like they have a dinner theater show, and I'm like, I don't want.
I've never seen it. I went along.
They got like a dinner theater show of the Titanic, and you can watch it sink every night. And I'm like,
A little bit.
I mean, that's like going to the Alamo. I don't know. I just kind of feel like these like recreations of horrible events. Maybe it's not my bag, I don't want to. I don't want to see all that. Yeah, but I mean, maybe they got some of the things that were from the Wonders exhibit. Oh, okay. Yeah, it was pretty cold. Yeah. It's like, ugh. So I'm a, it's pretty terrible if you want to really dive into what it's like to be stuck in open water and not know if you're going to live or die. There was one thing that happened in World War II. Yeah, the Indianapolis. They made a documentary about that. The Indianapolis sunk. It was like on a secret mission. Yeah, it was delivering stuff somewhere, but the Indianapolis ended up sinking, and they didn't. Nobody knew that they were out there because it was a super secret mission. So you had a bunch of soldiers just floating in the water, getting eaten up slowly by sharks. Yeah,
Can't remember how long it took.
took like 2 days, I think. It's just woo. You sit there, sitting next, stand, floating in the water, and you got your friend Billy. Now Billy is just half of them's gone. It's like woo. You can always count on nature to be nature. So, all right, let's talk a bit about that osmotic pressure. Osmotic pressure, that variable, sometimes they represent it with a pi symbol or like a lowercase italicized p. You can see either one of those with osmotic pressure. We look at molarity, not molality. So molarity is basically moles per liter. That's amount of stuff, right? It's concentration. Our constant, this is our gas law constant. And depending on your pressure value, that's the one that you're going to pay attention to. So you want the gas law constant that has the pressure value that matches your pressure for osmotic pressure. Pay attention. So pressure value units, like you're going to have to look at that. And then the temperature is almost always in Kelvin because the gas law constant is in Kelvin. So the units that you're going to want to pay attention to on which gas law constant to use, I always give you your constants. I tend to just stick with atmospheres because that's easy. You're going to have moles, liters, Kelvin, and either atmosphere, torr, bar, millimeters, mercury. There are so many different versions of the gas law constant, but the one that you're going to want is moles, liters, Kelvin, and whichever one of these has to deal with the problem that you're working on. So, what are the things that affect osmotic pressure? How much stuff you have, and what the temperature of the water is. Those are the two main things. This is a constant, so that doesn't change. So this stays the same. You mess around with the temperature, you're going to affect the osmotic pressure. You mess around with the concentration, you're going to affect the osmotic pressure. Just as an aside, something in nature that didn't kill people but was still funny. Did y'all hear about White Gladys, the orca that was sinking yachts off the coast of Spain? Another reason why I love nature. They think Gladys got traumatized by a yacht. And so when she went back out, she's tracked. There's a lot of scientists that'll track orcas because they want to check their migratory patterns and see what they're doing and all that. Well, White Gladys, she was one that scientists were tracking. And they noticed that she had some scars on her. And they were thinking, okay, what's going on with this? What's going on with this orca? And then they noticed, wait a second, we got some sinking ships that are happening right outside of Spain, on the coast of Spain, yachts, like people with money going out deep sea fishing. Gladys was sinking their yachts. And not only was she sinking their yachts, she was teaching the other babies how to do it. So we got like one of the tutors came up with this particular. I think Will came. I was talking to them about Gladys. And so he called it organized crime. So this is like orca gang violence. But they're teaching other orcas how to sink yachts. And it's real easy. I mean, they can just flip it right over. You bang on the side enough, you can capsize a yacht and it'll sink. So it's organized between the orcas in different pods. And the orcas tend to have a matriarchal society. So the mom, like the head lady orca, will teach all the other little ones how to sink stuff. So y'all, nature's cool. Not the second one. I saw the first one. Yeah, they do that. I mean, there's so much stuff that animals do. It's just unreal. If you're ever bored, look up old world monkeys destroy cars in India. It's great. Okay, I'm going to erase here. We're going to start working on problems. A lot of the old world monkeys, they work in gangs. They go and rob stores. They like steal food out of convenience stores. There's one group, because when you go to India, they have like beautiful jungles and all these cool looking places. People will be driving in their rental cars and they'll see this cute little monkey out in the middle of the road sitting there pulling like one of them Puss in Boots thing. Looking, oh, look, it's so cute. It's just sitting there. So they get out of the car and they're like, oh, let's take a picture of the monkey. And then his friends are hanging out in the trees. And then they jump the car and start stealing stuff. They will destroy your car. It's great. Well, it's not great, but it's fun to watch. It's so funny. Okay, let's go to here. Woo. It is a lot of fun watching stuff like that. It is pretty funny. Maybe I shouldn't laugh, but you know, hey. They're just hanging out. There was one wildlife photographer who won an award through National Geographic because, oh gosh, I forgot the type of ape it was, but one of the apes grabbed his camera, stole his camera, went back to his little flat, where the little ape lived, took pictures of everything and made selfies. It was great. And then PETA sued the photographer because they felt like the chimp should have rights to the pictures. That's why I can't take PETA seriously. Yeah. It's just weird. Mhm.
Yeah, he looks into the camera and he's eating it. Not every day, like he goes and grabs it apparently every day. Stares into the camera.
It's like, I love nature, man. Okay. Let's put this into practice. So let's do 13.89. So we've got a 0.100 aqueous solution of the base HB, hydrogen boride. I think that's boron. Has an osmotic pressure of 2.83 atmospheres at 25% or 25 degrees Celsius. Oh, I don't want to calculate the percent ionization of the base. I'm just going to use these numbers and we're going to do something else. So let's figure out what the temperature it's at. So my question is, what is the temperature of this solution if it has that reading for osmotic pressure? Oh, wait, no, it is at 25 degrees Celsius. This has got all the information already for it. I don't want to do that. I'm just making another one. Forget that. So what is it asking? So if I have a solution that's a 0.5 molar NaCl solution at 25 degrees Celsius, what is the osmotic pressure? I'm just going to make up a problem. I feel like that's most of my life. It's making up problems. Not just in class. Osmotic pressure. So we're looking for the osmotic pressure of a salt solution that's 0.5 molarity, 25 degrees Celsius. So my plan is to use the molarity equation, which is, the osmotic pressure equation that has molarity times the R constant times the temperature. So I've got the molarity, which is 0.5. I need to look at my R constant, and I need to convert my Celsius to Kelvin. So I've got to convert Celsius to Kelvin. So how I remember my conversion for that is Celsius lives on 273 Kelvin Street. That's how I remember it. So 273 plus 25, 298, right? Okay. So this didn't tell me what unit it wanted my osmotic pressure in. If it said, what is the osmotic pressure in atmospheres, then I'm going to need the R constant for atmospheres. If it is, what is the osmotic pressure in bars, I'm going to need the R constant for that. So let's have a look at, I know I've got gas law constants. All right. It's good to just have a table of it sitting around. Notice all of these different units. You can use the gas law constant for all kinds of different things. We've got torr, psi. If you want to use old English, cubic feet instead of liters. Just lots of stuff. We have a gas law constant associated with energy, joules. So the one that we're going to use is the liters, atmospheres, Kelvin, and moles, because those units match up with what I'm doing in my problem. So it's 0.082057. So that's here. 0. I swear I'm going to get this tattooed on my arm. I use it so often. 0.08207. 057. Okay, is that right? Yes. Okay. And then my temperature is 298. All right, so let's see what we end up with. Now I just got to multiply. And if it's biology, multiplication and division are the same things, right? Multiplying cells, dividing cells. Yeah, I got 12.23. Is that okay? Yep. We could just do the one because so 0.2 atmospheres. Okay. So do y'all know what that feels like? You're feeling 1 atmosphere right now. So if you felt 12 atmospheres, it'd be 12 times the pressure that you're feeling right now, which is hard to kind of take into consideration. I want to know what atmospheres are at the bottom of the ocean. Now I want to know that. Of pressure at, I want to know what that osmotic pressure is. Oh. 1 atmosphere at the surface to 1,100 atmospheres. I guessed about 1,000 atmospheres. Anything except metric. 100 elephants on your head. Anything but metric. But, to be fair, I don't think people sit around thinking, 1,100 atmospheres. What's that feel like? 100 elephants on your head. Oh, yeah. So 100 adult elephants, not even the baby elephants. Baby elephants are about 250 pounds. That's a lot. Whoa. So it increases by 1 atmosphere every 10 meters. That's scary. So this gets into that. Yeah. So a meter is like one yardstick. So 1 yardstick is, yes, at 3 feet is 1 meter. Ooh, that's giving me a headache. 100 elephants on your head all at once. Yeah, if I had 100 elephants on my head, if that just all of a sudden happened, I wouldn't know what happened, right? That's just, whoo, okay. I'm gonna have to have some Tylenol or something after this, thinking about that. Let me see what else we gotta cover. So let me do one more problem for osmotic pressure. Yeah, that's all I really want to worry about with that. So let's do one more problem with osmotic pressure. So the cool thing about this equation is you can determine any of these particular things as long as you have at least 2 measurements. If you have the concentration and the pressure, you can determine the temperature because this doesn't change. If you have the temperature and the pressure, you can figure out the concentration. So let's do one of those. We'll just stick to salt. What is the concentration? What is the concentration of a solution, of a NaCl solution at 35 degrees Celsius and an osmotic pressure of, let's say, we'll say 150 atmospheres. Not quite below the ocean, like too far. About a tenth of the way down, I guess. I don't know. What do you think? So, first thing we do, what is it asking? I need to know what the concentration is. I'm going to pull up that image again. So y'all got your gas law constant. It's good to just have these. Did it open in the new tablet or tab or whatever? There it is. Okay. It's good to just have one of these in your notebook. All right. So what is the concentration of a salt solution at 35 degrees Celsius and an osmotic pressure of 150 atmospheres? What's your plan? So we can rearrange the equation in advance if you want to. Right? I got this right over there. Sometimes when I see variables, I freak out. So if you're a person that freaks out with variables, then rewrite the equation in words. I find it less threatening if I write it in words sometimes. So I've got like molarity is equal to R constant times temperature in Kelvin divided by osmotic pressure. So what do y'all think? $0.17? What did y'all get? So 308 times that divided by 150. Calculator times so I got 0.17 as well. So that's 0.17. So let's play around with that for a second. So the molarity is equal to 0.17, right? Let's try this. Let's play around with this. What if the temperature changed? What if my temperature was 80 degrees Celsius? And I keep the molarity the same. So this is my temperature. I'm going to have to add 273 to it. I want to know what the new pressure is. So let's say we keep the molarity the same. We change the temperature of the solution. Let's say we heat it up. And now we want to measure what the pressure is. What's the new pressure? Let's see what happens. Yes.
Approximately 4 and 9,300. I'm added it by 173 instead of 173.
Okay, so that's the Kelvin.
That's what I got for off.
Oh, okay. Okay, so what we get? 4.9? You got 4.9? Okay. So we got 4.9 in atmospheres. What happened to the pressure? So it dropped. So when we heat up stuff, it can affect the osmotic pressure as well. If we keep the molarity the same, we keep everything else the same, and we start messing around with the temperature, we can affect the osmotic pressure for that. Yeah, it would seem so. Yeah, I would say so. Yeah, that's how the math works out. So, alrighty. So let's have a look at where we're at with these. Okay. Concentrations of solutions. How are y'all with freezing point depression and boiling point elevation? How are y'all on the calculations for that? Do you want us to go through that again? Yeah? Okay, let's go through that again. All right, I'm gonna erase right here. Okay. Let me redo. I'm just going to see if I can find a problem in the book over here that we can do together. Here we go. Alrighty. Vent, solution, molar mass. I don't know if this, let's go back here. Let's go to colligative properties. Okay. Okay. That's all about vapor pressure. Okay, boiling. Okay. Okay. So let's look at 13.62. I think we did 13.63 already, right? Let's do this one. What are the boiling points and freezing points of a 3.12 molality? So that's molal. The little m means it's molality solution of naphthalene and benzene. The boiling point and freezing point of benzene are 80.1 and 5.1. Okay, so what is our solvent in this case? Is it water?
Naphthalene is being put into benzene. Benzene's solvent and
Naphthalene. This stuff stinks. It's like what mothballs are made of. So naphthalene is your solute. Benzene is your solvent. So we need to know what the boiling point is and what the freezing point is at once we start making a solution together. Okay, so this is actually two problems. Freezing point depression and boiling point elevation. So I'm going to need the same equation, A times the molality. Is that it? Yeah, but I don't think they have one here. It's just one. We'll just assume it's one. If I give you if there's a Van Hoff factor involved, I will let you know. I will give it to you. Okay. So we're just going to assume that the Van Hoff factor is 1. So we're going to need this, and we're going to need this. So my plan is to use the freezing point depression and boiling point elevation equations to get what my boiling point and my freezing point of that solution has to be. To get BP and FP of my solution, right? So I've got naphthalene. Maybe I'm having a hard time visualizing this. Naphthalene is going into my benzene. So if it helps you to draw pictures, that can help. So this is my solute, and this is my solvent. The biggest part of doing a problem is the planning. The planning is what you should spend the most time on. So my plan is to use this. I've got to get my new boiling point and my new freezing point. And I'm looking at benzene, not water. And I'm looking at naphthalene as my solute. Okay, So, what's the information that they gave me? I've got molality and a boiling point and a freezing point. 3.12, is that right? And then I've got a temperature. My boiling point is 80.1. Okay, so 80.1 is my boiling point, and my freezing point. Let me try to spell. Ugh. My freezing point is 5 degrees. Is that it? 5.5. Okay, 5.5, and this is in Celsius. All right. So I've got like my initial, but I don't have my final temperature, right? Well, what I'm going to have to do is figure out what my difference is. So the change in temperature is what I'm calculating for. So the change in temperature is when you take your initial and your final and you subtract, right? So I'm going to get that number here. So I should be able to back calculate and figure out what the new boiling point and the new freezing point is going to be. My boiling point should be higher than the 80.1, and my freezing point should be lower than the 5.5. All right. So now all I got to do, there's something I don't have. I got to look this up. I got to look up the KB and the KF of benzene. Okay. So KB and KF of benzene. I will always give you constances. Okay, here we go. All right. Let's see. KB of benzene. All right. So the KB for benzene is 2.25. 2.25. Wait, 2.52? Okay. Now let me look up the KF of benzene. Okay. 5.12. Is that in Kelvin? We need it in Celsius. Hold on. Was the other one in Celsius or was it in Kelvin? Wait, hold on. No, that's kilograms, moles, that. Okay. So yeah. So we need to make certain our units are right. Okay, so there's two different ones. So this is in Celsius. We're going to go with the Celsius ones because that's what we got these in. So the KF is 5.12 and the KB is 2.53. Yeah, so 2.52 and this is 5.12. Okay. Because units matter. We got our thing in Celsius. So we're looking at Celsius. So we've got Celsius for our freezing. Okay. So now that I got that, so this is for, sorry, the KF and the KB, not that. Okay, so this is here, KF, and this is here, KB. So let's do one of these at a time. So I'm going to do the freezing point first. Change in freezing point is equal to the KF times the molality. So that's 5.12 times 3.12. So what does that give me? Is that right? About that? Okay, let's do the same thing. Here we got 2.52 times 3.12. Is it 5? Okay, 5.3 is fine. You'll probably get pretty close to the same. So what did y'all get here? 889? 89. Okay. Okay. So now I've got the change in freezing point, and I've got the change in boiling point. So the freezing point I expect to drop, right? So if we've got a freezing point of 5.5, I'm going to erase this right here. We got a freezing point of 5.5, and we expect it to drop minus 15.97, right? Because that's the difference. That's what the change is in, right? That's the difference between the two. So our freezing point of the solution is going to be 10 what? 47. So if I wanted to, I could again go backwards and do what's my change in freezing point? I should get that number again, right? So this is the new freezing point of that solution. What's the new boiling point? We got 80.1, and we're elevating, right? We're raising that temperature, so we're going to add it. 80.1 plus 7.89, 87.99 is our new boiling point of the solution. So the majority of my time was spent coming up with my plan. Because this is just multiplication, addition, and subtraction, right? But if you don't get the right numbers here, just plugging in the numbers, the correct numbers, you're going to get a very wrong answer. So what did I do? The first thing I did was figure out what it's asking. It was asking me the new freezing point of the solution and the new boiling point of the solution. What it gave me was the freezing point and the boiling point of the benzene. What I had to look up were those K values of that freezing point and that boiling point. Then I used the same equation, plugged in those numbers, got my change in temperature for the boiling point, change in temperature for the freezing point. Then I remembered freezing point drops, so I'm going to have to subtract. Boiling point goes up, I have to add. So I had to do. So it's a little complicated, but I probably won't give you like something heavy like this. I would just be like one of them, right? Okay, it's 11:44. I'm going to cut off the live stream. If y'all need to go back and look at this